We have solved several problems on the design and analysis on beams. In this math, we'll go through the serviceability condition of beams. First of all, we have to select the W section, and we have to check serviceability for the deflection. You have a deflection limited deflections. You cannot go over the limited deflection criteria here, and you have to check the shear that is occurring on the beam also. So there are two checks. One is for deflection, and another one is for shear. First thing first, you need a moment. So we'll find out the moment that is occurring on on this structure. That is the moment will be. You have a dead load of 0.5 kip per feet, and you have a live load of 1 kip per feet. And you can see that the dead load is not including self weight. So you can assume a self weight of say 100 pound per feet. So that is actually zero point 0.1 kip per feet. So for that, we'll find the moment, that is W L square over 8. So here the W would be zero point 0.5 added by 1 and added by zero point 0.1. So that is actually 1.6, and you have a span of 42. So that is actually 42 squared over 8. So the moment that is coming on this structure is 352.8 kip feet. And the nominal moment, since you're using AST method, would be 1.67. That is actually a factor, and multiplied by 352.8. So the nominal moment would be 589.2 kip feet. To select a particular section, you need to know the uh, plastic section modulus. And let's say we're considering compact section. Considering compact section, if you consider that, then your Mn would be equals to Mp, and for that you have an equation of Fy Zx. From here you can find out the value of Zx. That would be Mn over Fy. In this math, Mn is 589.2 kip feet. I will convert it to kip inch, and I'll divide it with 50k. So for that, I'll have an a ZX value of 141.4 cubic inch. And to select a particular section, we'll select we'll bring another criteria for from deflection, that is the limited deflection is L over 360. And if you have a util load, let's say, and you have a simply support right over here, and if you have a simply support right over here, and you have a UDL of W, and you will have a maximum deflections at right over here. Let's say the deflected shape would be like this, and the deflected value at mid section is delta, and this delta value which is actually max value at midsection, will be equals to 5 384 multiplied by the UDL you have, the span length L to the power 4, and modulus of elasticity of steel or materials, and the I value. So from here we'll find out the I value since we will limit deflection. So in this case the del max will be equals to L over 360. So we'll find L over 360 value here. The L is 42. So if I multiply with 12 and divide by 360, I'll get a value of 1.4 inch. So the maximum deflection the beam can be given, that is 1.4 inch. So from here we can find out the value of I, which is moment of inertia, and that is actually about strong axis. So the I value would be 5 384. W would be here, and W is, this W is for service live load only, no other load. In this case, the live load is 1 kip per feet. We'll convert it in 1 kip per inch because we want to know the moment of inertia in terms of inch to the power 4. So this is the W, and you have a length of 42. We will convert it to inch, and you have E value which is 29,000, and you will have delta in place of I because we cross multiplied or the side was changed. So you have a del max of 1.4. So from here you can find out the value of Ix, and the value would be 1724.5 inch to the power 4. So based on these two criteria, one is ZX, another one is IX, we'll select the W section. You can select several sections, but for this math, I'll try this section right over here, and you can see that the ZX value is 221, and in our case we need a ZX value of 141.4, and we have a 200 sorry 2070 IX value, but we need 1724. So this value satisfies our criteria. You can select other sections also. So let's say our section is primary selected section is W2193. You can check whether it is a compact section or not. I checked it earlier. It is a compact section. You can check compactness. For that, you need BF over twice PF value, and you need another criteria, that is uh, we can it is actually your lambda. For flange you need lambda for wave. You can get these two values directly from the AIC manual under compaction criteria. We'll see that just now. Oh god, it's taking too long time to open. Damn. Okay, you can see that the DF over 2TF value is 4.53, and the other one is 32.3, which is H over TW. So one is 4.53, other one is 32.3. So this is 4.53, other one is say 33. So you can check this value with 65 over root over fy. In this case, fy is 50. For that, you'll get a value of around just around 9.15. So you can see that your uh, lambda value is less than the maximum lambda value it can get for a plastic moment. So uh, your lambda w, which is another criteria, is for that the maximum value it can be 3.76 root over e over fy. If you put the values right over here, you'll see that this value is way greater than lambda w value. So from here you can say that the thing we assume that the section will be compact section and the formula we use for compact section is okay. So now the other two things that is you need to check that the section is okay for shear. So the shear that is actually coming at this mid the shear, maximum shear actually comes at support, and that is V is equals to WL over 2. So in this case, the W is actually 1.593. How? Because 1 was for live load, zero point 0.5 was for dead load, and for the section we have a self weight of 93 pound per feet. So if you divide it with 1000, you will get 0.093. We just added that, and you have a length of 42. So you just can multiply it with 42 and divide it with 2. So you will get a share of 33.5 K. So we need to see that if the section is okay for shear or not. We have uh, we have to check that if our h over tw value, which is in this case, this is actually h over tw value, which is actually h over tw value was 37.2. I don't know whether I write it correctly or not, but the value was actually 37.2. And if this value is less than 2.24 root over e over fy, then you have a nominal shear capacity equation that is valid for under this condition, that is 0.6 fy aw. Aw is actually the cross-sectional area of wave. So that is actually the depth of your wave and the thickness of your wave. You can check this criteria. You can put the value of E and Fy, and you will see that this value is greater than this value. So this formula is valid to find out the nominal shear. So the nominal shear would be 0.6. You have a Fy value of 50, and you have a depth is 21 inch. It is 21.6 inch, but you can use 21 inch, no problem. And you have the thickness of your wave is 0.58. You can find it in the AIC manual. I will not open it right now because it takes time, and you'll get a value of 375.8 K. So you can see that, and you have to find out the reduced one, which is conservative one, and for shear divide you will just divide your nominal shear with this constant, that is actually 1.5, and for that you'll get a value of 250.8 cube. Still, you can see that this value is way greater than the value of shear that is actually occurring on the support of your beam. So now we can see that the section we have selected is okay for serviceability condition. So the section is W2193. So that's the math which is on serviceability condition of beam. We'll do two more maths. One is on shear and another one is for, I forgot that, but we'll do.